All right, everyone. Welcome back to the Algebraic Graph Theory Seminar. This week we have Julien and Sorci, who's going to be talking about quantum locks on Cayley graphs.
Alrighty, thank you guys all for having me here today. I'll just thank the organizers for letting me talk to you guys. So really excited to be here. Like you said, I'm going to be talking about quantum locks on Cayley graphs. A lot of what I'm going to be talking about is part of joint work with my advisor, Dr. Peterson. Before I even get into Cayley graphs, I'll get into that later on. I'll first want to tell you a little bit about what a quantum walk is. There's a lot of sort of quantum mechanics kind of happening in the background. And so I'm going to try to avoid as much of it as I can and just give you the kind of like the basic details so we can move on to the things we'll be looking at. So we're going to suppose that we have a collection of qubits. And all you need to know is that a qubit is, say, something that can hold information. And we'll suppose that we can take qubits and we could couple them so that if they're coupled, then they kind of interact and will share their information with each other. And now if I get a bunch of these qubits together and I couple some of them, I choose not to couple some other ones, then the information that I put into this system will evolve over time and kind of move around between them. And so to kind of model this mathematically, what we do is we take a graph and associate it to it. So we'll define a graph X whose vertices are the qubits, and then we'll connect two qubits by an edge if we couple them. And so this dynamical process we kind of end up with this information moving around is sort of this quantum analog of a random walk on this graph. So we can think of having sort of this like quantum walker, which is like information, and it's moving across the vertices of this graph based on the couplings that we chose. And now the fundamental question we're going to be asking is, can we couple the qubits so that we can get some nice states to come out of this sort of dynamical process? Okay, and I'll make this a bit more precise in just a second, what I mean about when I want things to be nice. To get in more of the specifics of what this walk exactly looks like, so like with a classical random walk on a graph, there's both a continuous time and a discrete time quantum walk. And so today I'll be talking about the continuous time model. And so in this case, there's this differential equation in quantum mechanics called the Schrödinger equation. And that tells us how these states will evolve over time. And the solution to that gives us the transition matrix for the walk. So if our graph has adjacency matrix A, then the transition matrix for the walk will be this exponential of ITA, which we'll denote by U sub A. And so here T is a time parameter. And so this matrix exponential tells us how our quantum state will evolve over time. And now since our adjacency matrix acts on the vertices of the graph, then this transition matrix will also act on the vertices of the graph. It also has complex entries, and you can easily show that it's a unitary matrix. Now in particular, if I give you, say, a quantum state that maybe I'll call x naught, which lies in C to the n, then to find out what the state of the system is at, say, time t, then I just take the transition matrix at time t and I multiply it by this initial state. Okay, so this tells us exactly how our quantum states how our quantum walker moves along the graph. And so now to get into what kinds of nice things we might like to happen, one of them is called perfect state transfer. So we'll say that our graph X admits perfect state transfer from the vertex U to the vertex V at time tau. If at time tau, our transition matrix has its youth column looking like some complex multiple of the Vth standard basis vector. And so what this means in terms of information is if I put my quantum walker on the vertex U, then at time tau, I should find the quantum walker at the vertex V. And so to give you a little picture, say we have just the path of length 3. and say this red dot just represents me putting the quantum walker on this vertex, then if I wait until time tau, then the walker has moved all the way to the vertex V. And so in a certain sense, the information is sort of being transferred from the vertex U to the vertex V. Now in practice, we like to be able to get perfect state transfer between vertices that are very far apart in the graph, because this kind of represents transferring information across long distances, which might be important in applications. And also, we wouldn't want our graph to be too big and complicated. So the best situation we could hope for is that we'd have perfect state transfer between the endpoints of the path. But unfortunately, it's known that only the paths of length 2 and 3 are the only paths that admit perfect state transfer. So this led a lot of people to ask, well, what other graphs could we find that admit perfect state transfer? In general, it's known that finding graphs that emit perfect state transfer is not an easy task because it's rather rare. So Chris Gautzel showed that if I fix a positive integer k, then there are only finitely many connected graphs with maximum degree at most k, which admit perfect state transfer. So this means that once I bound the maximum degree of the graph, then there are only finitely many graphs that will admit perfect state transfer with that maximum degree. And now kind of in the direction that I'll be interested in the literature for Cayley graphs in perfect state transfer, most of the research has been focused on the case of abelian groups. And now if you're interested in group theory like I am, you know that there are a lot of other groups aside from abelian groups. So it might be kind of natural to ask, well, what does the situation look like if we start considering non-abelian groups? And so that's what I'll be getting into in just a little bit. Now, before I start talking about Cayley graphs of these non-abelian groups, I'd first like to go into some kind of known results that we'll be using later on. So firstly, I'll sort of describe this spectral approach that you could take to try to determine when a graph admits perfect state transfer. And so the main tool here is to utilize the spectral decomposition of your adjacency matrix. And so if my adjacency matrix of my graph is, say, A, then since it's a real symmetric matrix, we can always write it as a linear combination of projections onto the eigenspaces. So here, the theta sub j's are the distinct eigenvalues of the adjacency matrix. And then this E tilde sub j is the projection onto the theta j eigenspace. Now, these E tilde sub j's, since they're projections onto eigenspaces, then they are orthogonal idempotents. And so because of these algebraic properties, then you can then take your transition matrix and you can also write it as a linear combination of those same projections. Now, if we kind of play around and assume that we have perfect state transfer, we can see that we can actually say some things about the spectral decomposition as a result. So assuming we have perfect state transfer from U to V at time tau, let's go ahead and we can put in the transition matrix on the left-hand side. We put in this, this sum of projections on the left-hand side. And on the right-hand side, we use the fact that the projections sum to the identity to kind of just insert them on the right. And now, since these projections are orthogonal idempotents, and if I take an E tilde sub j and I multiply it on both sides, it kind of kills all the other terms. And then you end up with that the jth term in each sum have to be equal to each other. And so we get that this equation holds for all j. Okay, and now the next step here is maybe a little bit technical, but the main point is that we observe that these projections, the E tilde sub j's, are real matrices, but this exponential here and this lambda here are both complex numbers. And so the only way for this equation to hold is if the uth column and the vth column of these E tilde sub j's are all equal up to a sign of plus or minus. Okay, and so that's one consequence. Another thing that has to happen is that these exponentials have to be equal to plus or minus lambda for most j. And like I said, there's a little bit of technicality here, but I'll get into what exactly I mean by most j in just a second. But the main idea that I'm getting at is that from assuming you have perfect state transfer, we see that we have a few consequences about the spectral decomposition of our adjacency matrix. And so now this kind of motivates a few definitions. So we'll say that vertices u and v of our graph X are strongly cospectral if that first equation held for all j. Okay. And secondly, we'll kind of make more precise what I meant by most j in the previous slide. And it turns out the notion is the eigenvalue support of your vertex u, which is the set of eigenvalues theta sub j, where the corresponding projection has its uth column being non-zero. And so when I said for most j in the previous slide, what I really should have said is all those j's whose corresponding eigenvalue lies in the eigenvalue support of u. And so when we're talking about perfect state transfer, a lot of the things you like to say about the eigenvalues usually have to do with the eigenvalue support. And so the eigenvalue support is kind of your set of kind of important eigenvalues when it comes to perfect state transfer. And so there's a known result that I'll just quickly mention because we're going to be using it later on when we start talking about Cayley graphs. And so this came from Gabriel Coutinho's PhD thesis in 2014. And so he gave a nice characterization of when a graph admits perfect state transfer. And since we're only going to be looking at regular graphs today, I'll just be stating it in that case since he gave a much more general result. But he showed that a regular graph admits perfect state transfer from u to v if and only if. Firstly, the two vertices are strongly cospectral. Secondly, the elements of the eigenvalue support of u are all integers. And then also certain number of theoretic conditions had to hold on the eigenvalues in the eigenvalue support of u. And lastly, he also gave a formula that told you what the minimum time of the transfer was in terms of the spectrum of the graph. And so the big takeaway from this theorem is that all three of these conditions, they all have something to do with the spectral decomposition of your adjacency matrix, right? Because the first condition had to do with the projections onto the eigenspaces. And the second two conditions had to do with certain eigenvalues in your graph. And so in theory, if I know what the spectral decomposition of my adjacency matrix is, I should be able to tell you if there's perfect state transfer or not. Okay, and so this will be important later on. And so now to get into the actual kinds of graphs that I'd like to look at today. So first I'll just define real quick the types of graphs. So we're looking at normal Cayley graphs. So here G will be a finite group. And we'll assume that its conjugacy classes are K0 up to KD. And now take your favorite conjugacy classes and we'll union them together and we'll call that set S. And now the Cayley graph of this group with this set, with respect to this set S, is the graph whose vertex set is the group G. And then we connect group elements of the form G and GS by an edge. Now, of course, you could consider more general Cayley graphs. So these Cayley graphs where our connecting set is a union of conjugacy classes, these are sometimes referred to as normal Cayley graphs. And so these are the types of graphs that I'll be considering today. And we'll see that these graphs have some nice algebraic properties that'll make it a little bit easier for us to determine when they admit perfect state transfer or not. So to move along with the theory, to kind of support this sentiment that they have some nice algebraic properties, one thing that's nice is that the irreducible characters of the group afford the eigenvalues of the graph. So for each irreducible character chi, it gives us an eigenvalue of the graph, which is this character sum over the connecting set. Which is great because now I can, if I know what the character table of the group is, then in theory, I should be able to compute the eigenvalues of the graph. One other thing that'll be helpful in just a second is that our adjacency matrix can be written as a sum of regular representations over the elements in our connecting set S. So here rho is the regular representation of our group G. And it's not too hard to show that this sum of regular representations acts in the same way as our adjacency matrix. Now, it'll actually be helpful for us to break up this sum down here over the different congruency classes, since we took S to be a union of congruency classes. So kind of moving in that direction, we'll define A sub j to be the sum of those regular representations that come from elements in the jth congruency class. And so with this notation, our adjacency matrix is now a sum of certain AIs depending on which congruency classes we chose to take in our connecting set. And now let's look at the collection of all of the AIs for all of the congruency classes. And then let's look at the complex matrix algebra that's generated by that set. It's sometimes referred to as the Bose-Mesner algebra. And now the algebraist in me is really happy because if you look at this, this complex matrix algebra, it's actually isomorphic to the center of the complex group algebra. And you can write down an explicit isomorphism that takes an AI and maps it to the sum of the group elements in the ith congruency class. So what this isomorphism is sort of doing is just kind of getting rid of the regular representation part. And now this is great because the center of the complex group algebra is well known to be a semi-simple algebra. And it has this set of orthogonal idempotents that are afforded by the irreducible characters. So the characters are doing a lot of work for us. Namely, if we take a character chi, then it gives us this idempotent that we'll call E sub chi, which is this big weird sum here lying in the group algebra. And now technically this thing, this E sub chi, it lies in the group algebra, but because of the isomorphism that we have up here, I'll be kind of talking about it as if it were a matrix just by conflating it with its image in the isomorphism. So don't be scared if I do that. But now let's go back to our situation of our Cayley graph, and its adjacency matrix is a sum of these AIs. And let's use these idempotents to our advantage to talk about the spectral decomposition. So the first thing to note is that these E sub chi's are actually eigenvectors of the adjacency matrix. And so what I mean by that is if I take A and multiply by E sub chi, I'll end up with a multiple of E sub chi back again. And it turns out that the multiple is exactly the eigenvalue afforded by that irreducible character chi. And so one of the things that this tells us is that all the columns of E sub chi, again, thinking of it as a matrix, all the columns are eigenvectors for the adjacency matrix A, and the eigenvalue is theta sub chi. Now, one of the consequences is that we can take the projection onto the theta j eigenspace, and then we can write it as a certain sum of these E sub chi's. Namely, we can write it as a sum over the chi's that afford us the eigenvalue theta sub j. And now if you put this all together, then we have this kind of alternative description of the spectral decomposition in terms of this other set of orthogonal idempotents. And now this is really nice because now we have this sort of kind of spectral decomposition, and it's all in terms of the characters of the group, which will be really helpful for us. And so now there's a few things that you can do once you have this alternative spectral decomposition. So one thing that you can show very directly is that the eigenvalue support of every vertex contains every eigenvalue. I think this was already shown using other techniques, but like I said, you can compute it directly using this, this different description. Another thing that we did is that we gave precise conditions for when two vertices in a normal Cayley graph are strongly cospectral. And so we showed that this happens if and only if the two vertices differ by a central involution. And also, whenever two irreducible characters afford the same eigenvalue, then they sort of act on this, in the same way on this central involution. Okay, so this gives us conditions to figure out when vertices are strongly cospectral. And now one of the important things here that kind of jumps out at us is that if we're going to find a normal Cayley graph that emits perfect state transfer, then our group should contain a central involution. And so this kind of motivates us to a certain family of groups. Namely, we decided to look at the extraspecial groups. So let me give you some background on them, and then we'll start looking at their Cayley graphs. So group G is an extraspecial 2 group if its order is a power of 2, its center has order 2, and then also if G mod Z is an elementary abelian 2 group. And now you can define an extraspecial P group for any prime P where you just change out the 2 with a prime P, but we'll just be looking at extraspecial 2 groups. So I just gave you the definition here. And now if you're unfamiliar with what these groups look like, what I'd like for you to think of is that these groups are kind of close to being an elementary abelian 2 group. So in general, these will be non-abelian groups, but maybe if it's more familiar for you, it's kind of close to being an elementary abelian 2 group in a certain sense. Okay. And now why do we care about these groups? Well, since the center has order 2, there's a unique central involution in these groups. And so it seems like in theory that it might be a little bit easier to determine which vertices might be strongly cospectral based off of our result. And another, so some other things that'll be helpful for us is that the non-central connexity classes of the group G are exactly the non-identity elements of the quotient G mod Z. And now I like to think of things kind of geometrically. And so since G mod Z is an elementary abelian 2 group, we can alternatively think of these non-identity elements as being points in a certain projective geometry. And so when I start choosing connecting sets in just a second, and I start choosing non-central connexity classes, I'll often refer to it as just picking points in a particular projective geometry, which is kind of nice. Another small thing that I just wanted to mention real quick is that this integer m is even. So this m was this exponent here in the elementary abelian 2 group part. So it's known that that's even, so I'll just write it as 2 times some integer n. That's just kind of a small thing. Right. Okay, so moving along. So let's look at Cayley graphs of these extraspecial groups. So from now on, G will be an extraspecial 2 group, and we'll denote its central involution by Z. And now we'll fix a connecting set and S. And now S may or may not contain the central involution Z. But outside of that, we'll assume that it's a union of L non-central connexity classes. So these K of Xi's here are non-central connexity classes whose representative is Xi, and there are L of them. And now the characters of these groups are well known, and they're not too complicated as far as character theory goes. And so from the characters, you can compute the spectrum of these graphs. And it turns out that all of the eigenvalues are integers. So these are integral graphs. And you can write down the eigenvalues in terms of this parameter L here that I wrote, which was the number of non-central connexity classes we took. And then also in terms of this other parameter that I call EY. And to explain what that is, thinking of these representatives, the Xi's, as elements in this particular projective geometry, then EY is the number of those points that lie in the hyperplane given by Y. So when I write X sub I bar here, that just denotes its image in that elementary abelian 2 group. So it's just the number of these points that lie in the hyperplane given by Y. And now, once you have the spectrum, you can use the theorem, the result that we gave before to determine when two vertices are strongly cospectral. And it turns out that this happens if and only if, essentially, it's never the case that a linear character and a nonlinear character afford the same eigenvalue. Okay, and now this is great because for these extra special two groups, there's exactly one nonlinear character and the rest are linear characters. And so the second set down here just contains one element. And so it seems like it's rather simple to determine when two vertices are strongly cospectral.
Sorry, Julien.
Yeah.
Are you assuming that the connection set contains the central involution?
No. So
Okay.
yeah, no, I'm not. Yeah, so I'm not assuming that. So a lot of these results and stuff like the spectrum will depend on whether or not I decided to put the central involution in or not. But in any case, it's always going to be integral, and the eigenvalues are always going to be something that has to do with L and these EYs here. I just didn't write down exactly what that was or not. But in general, I can choose whether I want to or not.
Okay, thanks.
Okay, cool. Right. Okay, so now that we figured out when vertices are strongly cospectral, so now we're well on our way to determine when these graphs admit perfect state transfer. And so the idea is that we're going to use the theorem of Coutinho that I presented earlier. And so I'll give you first the kind of preliminary theorem of perfect state transfer, and then we'll kind of simplify it in a second. So it looks a bit messy, but we'll clean it up in just a minute. So we showed that these Cayley graphs admit perfect state transfer if and only if one of two conditions hold. And now they look a little bit messy, but the conditions just depend on whether or not I chose to put the central involution into my connecting set. And then once I make that choice, then I just need certain kind of number theoretic conditions to hold regarding this parameter L and the EYs. Okay, and so that's kind of what these first two conditions are saying. And so this is a lot simpler than the conditions of Coutinho's theorem. It all kind of collapses down to either one of these two things being satisfied. And the other thing is you can write down the minimum time of the transfer. Like I said, it looks a little bit messy right now, but in both cases, it's pi over some GCD. And now this GCD just came from Coutinho's formula. And it just depends on whether I put the central involution in the connecting set or not. But like I said, we can simplify this a bit, and we actually prove that these GCDs that occur in the minimum time are actually both powers of 2. And the way that we did that is we looked at these kind of smaller GCDs where we just look at these L minus EYs because those kind of occur inside of the GCDs. And so if we can show that the GCDs of these L minus EYs is a power of 2, then it implies that these integers C and D also have to be powers of 2. And so if you put that together, now we have a kind of simpler statement where we get perfect state transfer if and only if one of these two conditions hold that are kind of number theoretic. And then the minimum time is just pi over a certain power of 2 that depends on L. Okay. And now looking at this, if we want to try to cook up some perfect state transfer from this theorem, there are two kind of simple things that, simple choices of a connecting set that you could make. So the first one is, well, if we want to just satisfy the first condition, well, we could just take Z to be in our connecting set, and then we could take L to be even. So recall that that was the number of non-central quantity classes in our connecting set. And so if L is even, then this 2 valuation will just be 0 since L plus 1 will be odd. And so then this inequality will just be satisfied kind of trivially. And then you can do a similar thing if you choose, if you want Z to not be an S, and you just take L to be odd, and a similar thing kind of happens to satisfy the second condition. Now, if you do this, you do get perfect state transfer, but the minimum time in this case is only pi over 2. And so you might ask, well, could we do a bit better than that and get maybe some faster transfer to happen? And it turns out you can. And so what we did is we constructed some examples that come from partial spreads. So if you're unfamiliar, a partial n spread, an f2 to the 2n, is a collection of n-dimensional subspaces of this vector space, such that any two intersect in the 0 subspace. And so there are a lot of well-known examples of partial spreads. So it's not hard to come up with actual examples. But one thing that we showed is that when our connecting set is the set of points of a partial n spread, and if it has 2 to the n minus 1 elements, then these normal Cayley graphs of an extra special group admits perfect state transfer, and the minimum time is pi over 2 to the n. Okay, and so here again, I'm thinking of S using that kind of isomorphism that I mentioned earlier, or that kind of correspondence. I'm thinking of S as being a set of points in this vector space, and here it's the points of a partial spread. And so what this theorem is telling us is that if I'm okay with my group being kind of large and my graph being large, then I can get arbitrarily fast perfect state transfer, since the n here corresponds to the order of the group. Another thing that's kind of nice has to do with the complementary graph of the graph. And so one of the things we showed is that for these extra special 2 groups, these Cayley graphs will admit perfect state transfer if and only if the complementary graph admits perfect state transfer at the same time. And so this was a result that was pointed out to us by Ada Chan, and had to do with the minimum time being a power of 2, and also these groups having its order a power of 2. Right. And so lastly, one thing I'll say about these extra special, these Cayley graphs of extra special 2 groups regards the distance of the transfer. So we saw before that vertices are strongly cospectral if they differ by central involution. And so I kind of did this kind of quickly, but when I had that theorem about perfect state transfer, the transfer actually occurs between vertices of the form G and GZ, where G is an element of the group, and Z is our central involution. And you can actually compute the distance between these group elements of this form. And it's either 1 or 2, depending on if Z is in the connecting set or not. So if Z is in the connecting set, then obviously the distance will be 1. And then if it's not, then in that case, it'll be 2. So I guess we're not doing so well with getting transfer over large distances, but at least our previous result on vertices being strongly cospectral in this case is a little bit simpler than other situations you might look at. So that's all I want to say about perfect state transfer. And so now I'll talk just a little bit about instantaneous uniform mixing in these Cayley graphs. And here the story is a lot quicker. So we'll say that a graph is instantaneous uniform mixing at time tau if our transition matrix at time tau has all of its entries have equal modulus. And since it's a unitary matrix, then the modulus has to be 1 over square root of n, where n is the number of vertices in the graph. And so what this is saying is that if I put my quantum walker on a vertex in the graph, and I wait until time tau, then that quantum walker will sort of be uniformly distributed amongst the vertices of the graph. And so as far as Cayley graphs go, there's one known result that's kind of relevant to these extra special groups. So Cao, Wan, and Feng showed in 2020 that an integral abelian Cayley graph will admit instantaneous uniform mixing if and only if the underlying group is either an elementary abelian 2 group, elementary abelian 3 group, elementary abelian 4 group, or the direct product of an elementary abelian 2 group with an elementary abelian 4 group. And now, like I said before, these extra special groups can kind of be thought of as being very close to being an elementary abelian P group. And so since we have a few elementary abelian P groups that admit instantaneous uniform mixing, it's kind of natural to ask, well, are these extra special groups close enough so that we might end up with instantaneous uniform mixing? So what's going to happen in this case? And so what we did is we looked at a result of Adjacency in 2020, and she proved that if we have a graph in an association scheme that admits instantaneous uniform mixing, then there's a certain inequality on the eigenvalues of the scheme that have to hold. And so what we did is we reinterpreted this and looked at the case of Cayley graphs, and we showed that if a Cayley graph of an arbitrary finite group admits instantaneous uniform mixing, then the size of the supports of all the characters have to be at least square root of n, where n is the order of the group. And so observe that this result doesn't have anything to do with the connecting set. We just need that the connecting set is still a union of conjugacy classes. But other than that, this sort of necessary condition only has to do with the character table of the group. And so it's just telling us that if we're going to get instantaneous uniform mixing, then the characters of our group can't vanish too much. And now there's an immediate consequence that no normal Cayley graph of an extra special P group admits instantaneous uniform mixing. And it follows directly from this result here, because for the extra special P groups, there's always this nonlinear character that will vanish off of the center of the group. And that's too much and contradicts this theorem. Okay, so that's kind of unfortunate. So there's a lot of open questions from these results. So you can view these extra special groups as being certain extensions of elementary abelian groups. And so it might be interesting to look at other extensions and seeing what the theory looks like in those cases. In particular, there's a broader family of groups called special groups. And as the name might suggest, the extra special groups are also special groups. So it might be interesting to look at those groups. And then another thing is that, so this whole time, we only considered normal Cayley graphs where the connecting set was a union of conjugacy classes. And so it might be interesting to look at more general Cayley graphs where connecting set is just an arbitrary subset of the group elements. And so that's everything I wanted to say. Thank you for having me.
Thank you.
Yeah, so I'd be happy to answer any questions if anybody had any questions.
Ask a question?
Sure, of course.
You said that for the graphs with PST, the distance between G and G times Z is 1 and 2. What's the diameter of those graphs?
The diameter, I guess I haven't really gone and computed it. So far I've only really computed the distance between the vertices.
Okay. Okay. I'm just curious about what those graphs are like in the scheme.
Yeah, I guess I haven't computed too many of those parameters.
Yeah, okay. Thanks, yeah.
No problem.
Other questions?
Actually, about that, it's like, how do you get the distances 2 when the involution is not in the center. Is that trivial?
Yeah, so I guess it just follows from I guess playing around with some group theory. Yeah, so I don't remember exactly the argument. I think if you look at if you multiply GZ by itself or something like that, then there's like some nice canceling that happens. I could direct you to the our preprint. I have it over here. Whoopsie. I have it over here where you can find the argument that that we gave. I don't. It wasn't that complicated.
Okay. Yeah.
I don't remember exactly how it worked out, but yeah, it was essentially just like one line of just like some simple multiplication within the group.
Okay. Yeah.
Yeah.
I also wanted to ask about the PSD and the complement.
Yeah.
So I was just curious about the proof of that, because that's not I believe true in general for Cayley graphs or even normal Cayley graphs.
Probably not. Yeah, I guess the main thing was so you can write down so we have this relationship between the adjacency matrices of just your graph and then the complement, just like in general. And then from that, you can put that into your transition matrix, and you can get this kind of identity concerning the transition matrix of the complement. And I guess what ends up happening is there's like some nice things that kind of cancel, just because the order of the group is a power of 2, and this the minimum time in this case is pi over a certain power of 2. So just to give you the rough idea, that's kind of what ends up happening. Is like there's just some nice stuff that happens just because both of these things are certain powers of 2.
Okay. Yeah.
But yeah, I don't think that would happen in general.
So this is a very naive question based on your comments about abelian versus non-abelian and the value of having that unique central involution. But the obvious family of groups that occurs to me when you talk about that is dihedral groups whose order is divisible by 4. Has anyone looked at that?
Yeah, I know there's some results concerning dihedral groups. I'm not totally sure if it also includes those examples. At least with these extra special groups. So the dihedral group of order 8 is an extra special 2 group. So I guess that would be one such example. But yeah, I'm not totally sure about in general if maybe those groups have already been studied or not.
There is Cao and Feng, they have a paper on PSD and on Cayley graphs of dihedral groups.
Yeah, I remember seeing that, but yeah, I don't remember what exactly they proved there in that direction.
Yeah, there is some PSD sometimes. You can, I'm sure you can find it on the archive, but yeah.
Yeah, but other than that, I don't think anybody's really studied PSD and Cayley graphs of other non-abelian groups. At least I'm not aware of anything else outside of those dihedral groups. So as far as I know, these are kind of the first attempt at looking at it.
I think if you're going to look at Cayley graphs, non-abelian groups, you might as well just cut your losses and go straight looking at those transit graphs.
Mm-hmm.
I think if the group's not abelian, then being Cayley is not going to help you very much.
Right.
Do you mean if you're not assuming that the Cayley graph is normal?
Yes.
Right. It seems like that situation would be a bit complicated. So everything kind of worked out nicely when you're in the normal case, but yeah, I'm not really sure what might happen in the non-normal case.
You can't get the eigenvalues nicely, and so you're probably better off to use somewhat different machinery. But I don't know what that would be. But I said, once you go past normal Cayley graphs, I think you might as well look at Berg's transit graphs.
Mm.
I just found, I was searching for Chow and Cayley graphs on dihedral groups. And I just found this paper that I missed in EJC. The title is the perfect state transfer on Cayley graphs over dihedral groups, the non-normal case. This is 2020, this year.
Oh, okay, cool.
Yeah.
Is that
I
the
put
one
the
that
link. Yeah, I put the link
in the
on.
chat?
Yeah. I was
Okay.
actually looking for the an older one by them.
The dihedral case is a bit easier because the irreducible modules have dimension 1 or 2, and so that you can work your way through it. And so you can get information, but the argument is in those cases. This is why in discrete quantum walks you can handle the two reflection case, because you're looking at representations of the dihedral group.